Hello, and in this talk we'll be taking a look at how accurate the Shockley equation is in practice, and we'll be taking a first look at Zener diodes. You might remember the Shockley equation. It says that the current through a diode is equal to a constant called the saturation current of the diode times e to the power of the voltage across the diode divided by the ideality factor times a constant which at room temperature is about 25 millivolts. It's actually the Boltzmann constant times the absolute temperature divided by the charge on an electron, but it works out to be approximately 25 millivolts at room temperature. -1. Now if you plot this, you get a graph like this. You'll note that I've changed the scale between the positive y-axis and the negative y-axis, otherwise you would never see anything happening on the negative y-axis at all. We can try this on the simulator to see what it looks like with the same scale. Here I've got the voltage across the diode on this voltmeter, the current through the diode on this ammeter, and I'm going to plot the current against the voltage on this graph. I'll put it in automatic mode so it automatically takes readings as I change the voltage at the top point of the circuit here, and thus changing the currents and the voltages throughout the circuit. And we'll see what happens. And we get this. Well, as you can see, fill in a few more values. It is a very non-linear component. The current is absolutely not proportional to the voltage at all, and once you get down to about less than about 0.5 volts in this case, the current is, on the scale of this graph, effectively zero. You can't see any current at all. There is a tiny current flowing, but on this scale you cannot see it, compared to the milliamps that are flowing up here once the voltage across the diode gets to about 0.7 volts or so. However, if I do expand this scale, then I can show the effect of the Shockley equation on the currents in reverse bias. The fact that when you can neglect this term in the Shockley equation, which you can for large negative voltages, then the Shockley equation becomes approximately just the saturation current times -1, or minus the saturation current, which is exactly what's happening here. This graph is for a small signal diode, a typical small signal diode, which has a saturation current of 3 nanoamps. Now, if you look at the datasheet of the 1N4148, you can deduce that the ideality factor is around about 2. But if you then plot the current against voltage characteristic for the Shockley equation prediction against the graphs in the datasheet, then you get something like this. I've done this on a logarithmic scale of forward current, so you can see that there is very good agreement up to a forward voltage of about 0.8, which corresponds to a forward current of about 10 milliamps. So for all currents between about 0.1 milliamp and in fact below that, up to 10 milliamps, the agreement between the Shockley equation and the actual performance of the real diode is very good. But at higher currents, the two begin to diverge. The ideal Shockley equation should follow this almost straight line. And it's almost a straight line on this graph because I'm plotting the logarithm of the forward current against the forward voltage. Now, when I can neglect this -1, which I typically can for all reasonable forward voltages where I have a lot more than the saturation current flowing, then I can approximate the Shockley equation as is e to the power of v over n times 25 millivolts. And if I take the logarithm of this, I would get log of the current is approximately equal to the log of the saturation current plus the log of this term. The log of this term is just V over N times 25 millivolts. Well, that is the equation of a straight line. Logarithm of the current is a constant plus a gradient, in this case 1 over N times 25 millivolts times V. So I would expect a straight line if I plotted the log of the current, and I do, until we get to this point here at about 10 milliamps. And then the real diode starts to give less current than you might expect. Why? Well, it's because the Shockley equation only applies to the PN junction itself. But real diodes have a block of P-type near the junction region and a block of N-type on the other side of the junction region. And these are semiconductors. They're not particularly good conductors. They have a resistance associated with them. So a better model of a real diode, which incorporates the resistance of the rest of the body of the diode, and also some contribution from the leads and the junction kind of resistances, because you have to solder a bit of metal onto the P-type and the N-type in order to use it in a circuit, and these have resistances too. If we include those resistances in our model, we would end up with a circuit element that looked something like this. A resistance in series with a diode. And the diode obeys Shockley's equation, and the resistance obeys Ohm's law. If we include that in our formulation, then a resistor of about 1.1 ohms means that the two curves match each other very well up until the kind of currents flowing through the diode that would result in the diode probably overheating and melting. We can incorporate this effect in the equation quite easily by just taking the voltage across the entire diode, that's this, and calling that VD, and then determining that the voltage that we have to use in Shockley's equation, that's the voltage across the diode component only, is VD minus the voltage across the resistor. And the voltage across the resistor is the current through the resistor times the value of the resistor. And we'd end up with this equation here. It's not a particularly pleasant one to try and solve circuits with, but we'll be looking at techniques for how to do that a bit later on. Next, Zener diodes. Zener diodes have this controlled breakdown. An ordinary diode will have a exponential type characteristic of current against voltage in the first quadrant here, where both the voltage and the current are positive. But if the voltage across the diode goes negative, then the current will rapidly reach the saturation current and just remain there. A Zener diode, however, when it gets to quite a low voltage, will start to break down and conduct current in this reverse direction. And this line here can be quite steep, so that the voltage across the diode doesn't change very much, with quite large changes of current flowing through it. And this can be very useful, as we can make circuits which maintain a reasonably constant output voltage for a very wide range of input voltages. Here, for example, we can change the voltage at the top of this potential divider from 5 to 15 volts. That's a range of a factor of 3 in voltage. If this diode was a resistor, then we would expect the output voltage to change by a factor of 3 as well. But it doesn't, because at 5 volts, the output voltage 3.327 volts, when I increase this by a factor of 3 up to 15 volts, the output voltage only changes up to 3.7. So we have, for quite wide changes in input voltage, an output which doesn't change that much at all. We've stabilised the voltage. It's a way of producing a voltage reference, a point in the circuit that maintains its voltage no matter what the input voltage to the circuit is. Quite useful for battery-powered circuits, where the voltage that you get from the battery is decreasing as the battery discharges, but the voltage at this point in the circuit would remain comparatively constant and could be used as a reference to compare other voltages to. We'll see quite a few applications of this type of circuit in later videos as well. Okay, that's all for this time. Next time we're going to have a look to see how we can calculate the currents and voltages in circuits with diodes, non-linear diode components.